Hello, friends. Maybe I need to clip that first little section off there. This is a video for the multivariable calculus class. We didn't quite get time to get through a couple of examples that I feel like are fairly important ones. So this is my video working them out in case you weren't able to just figure that out or find videos where probably other people have done this as well. So, all right. So the questions we were looking at, and bear with me a little bit here as I get my iPad to show this up. Haven't done this in a little while. And apparently a plugin isn't required in order to do this. So, okay, now I should be able to just go ahead and so hit screen mirroring and zoom. Yay, there you go. All right, so as you can see on that, can I adjust the size? No, I can't. Okay, so this doesn't look quite like I anticipated it looking, but we're looking at finding a power series solution to the differential equation y prime equals 2y. And I'm going to add on there that y of 0 equals y sub naught. Were I doing this in class, I would have just gone ahead and said that. So it doesn't appear on the paper, but it is a part of the problem. So the thing that we need to do is to start out with this y prime equals 2y. And we're going to get more derivatives. Since y differentiating on both sides, wow, that's way too small. So let me back up on that a little bit. And we will just redo it much larger. So y prime is equal to 2y. Well, that means that if we differentiate on both sides, we're going to get y double prime equals 2y prime. And since y prime is equal to 2y, that means we will have 4y out of this. You can probably see where this is headed pretty quickly. So that means that we can go through and differentiate as many times as we want, and we will find out that the Nth derivative. So the notation for that, I said Nth derivative, sorry, Nth derivative. The notation we use for that is to put parentheses around the n to distinguish it from the nth power, is going to be equal to 2 to the nth power y. So the reason that this is important is that we are wanting to write ourselves a Taylor series for this. And as you'll remember, a sub n was going to be equal to the nth derivative evaluated at our center. Our center here is going to be 0, then divided by n factorial. So for our purposes, we know that we're going to get then 2 to the n times y of 0 divided by n factorial. And since y of 0 is 1, then that is going to be equal to just 2 to the n over n factorial. Oh, sorry, I said 1. I meant y sub naught. Just kidding. So now our power series, y of x here, that's centered around x equals 0, will go summation n equals 0 to infinity, 2 to the n over n factorial x to the n. Okay. Now, if you'd, and weirdly enough, I wrote a whole line there and it does not seem to have appeared on the share. So I'm going to stop share and try to reshare. But the notion that we're getting there, come on, no, not that. Screen mirror, zoom. Okay, now it showed the whole thing. So the notion that we're getting there is that we've got this power series, And if you go back and check the interval of convergence, which was not a part of the problem, admittedly, but if you check the interval of convergence on it, it's going to be super nice, because we'll be taking the limit as n goes to infinity. Absolute value on the bottom will go 2 to the n over n factorial, x to the n, dividing 2 to the n plus 1 over n plus 1 factorial, and x to the n plus 1. And then we'll put absolute values around that, of course. We're still taking the limit as n goes to infinity. Now, nicely enough, you will end up with 2 times an absolute value of x, and then divided by your n plus 1, because the n factorial and the n plus 1, wow, once again, it has stopped displaying. And then I have to start it again. This is the most annoying instance I've ever had of this. I think I need to reboot everything. So, but rebooting everything in the middle of a video isn't really practical. So, okay. So we end up with this limit, but remembering x can be any real number, but it has to be a fixed real number. This is going to get us a limit of 0, which is always less than 1. So the radius of convergence will turn out to be infinity, and the interval of convergence is going to be from minus infinity to infinity. Okay. In other words, this converges for all real numbers. So we're going to get a power series there, which if you're clever about it, you can spot that is the power series for e to the 2x. Except I forgot to write my y sub naught on there, but yeah, fill that piece in at your leisure. In any case, though, you're getting then a power series for y sub naught e to the 2x for your solution of y prime equal to y. If you did some differential equations in your Calc 2, you know there's another way to get at that. That's probably a little bit easier, but this is just demonstrating some of the power that you have with these power series solutions. So, all right, the next problem that we have, hoping that the share screen will not continue to be a problem here. But the next problem we have asks us to take a look at e to the I theta and show that it's equal to cosine theta plus I sine theta. So this is something that's referred to as the Euler Formula, and it's related to something else called de Moivre's theorem. But the Euler Formula there really has as its big emphasis I hit the wrong button yet again, that you can take this e to the x and expand it out and turn it into this cosine and sine portion. Now, if you're taking a look at the formulas for cosine and sine here, you see that they have power series that only have even terms for cosine and odd terms for sine. Not a big surprise since they're even and odd functions. But the thing is that that means that it feels a little, oh, damn it. Sorry, folks. It feels, it looks as though I left something out there again, and I'm going to fix that rather than just going blithely on. Both of those were supposed to have a -1 to the n appearing in them, and I forgot to do that. So let me just fix that real quick. Were it not for that -1 to the n portion, this this would very much look as though we could just split things up into those two pieces, into the even terms and the odd terms. And in fact, your power series that you end up with for hyperbolic sine and hyperbolic cosine do exactly that. They don't have the -1 to the n appearing in them. So the question that we had in class about what those were kind of has that connection, okay? That the hyperbolic cosine and the hyperbolic sine have the same power series, except without the -1 to the n, okay? Well, the thing that we're going for here, though, is that we need to deal with e to the I theta. So like we did with problems in class, we are just going to do a quick substitution here and have I theta to the n over n factorial, which isn't super informative. It's probably going to be more helpful if we break it out and write a few terms of it. So we will have, let's see, plus I theta quantity squared over 2 factorial plus I theta quantity cubed over 3 factorial plus I theta quantity to the 4th over 4 factorial. And as you can see, I'm running out of room there. But when I copy it down here and try to simplify, I'm going to remember that I squared turns out to be -1. And so that means that although I've got 1 plus I theta here, in the next one, I've got minus theta squared over 2 factorial. And then when you cube I, you'll have an I squared, which would be the -1, and still another I left over, theta cubed over 3 factorial. And then plus, because when you put I to the 4th power, it would be just 1, theta to the 4th over 4 factorial. If we continued on here, then we would have plus I theta to the 5th over 5 factorial, and so forth. And the nice thing about this is that if we were to take just the even terms and pull them out, and just the odd terms and pull them out, we could place them into 2 different series. So the first one would go 1 minus theta squared over 2 factorial, and then plus theta to the 4th over 4 factorial, and then minus theta to the 6th over 6 factorial, plus ... And then the other one would go I times, I'm just going to factor an I out to the beginning, theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial, and then minus, and it will continue on from there, okay? So if we look back at the definitions of, not definitions, the power series representations, we have cosine theta in the first one. In the second one, we have sine theta, okay? And just like before, we end up getting an interval of convergence that's the whole real line. And we have that formula broken out there. Nothing seemed to go wrong with the sharing for a change. The nice thing that comes up with this identity is something that we refer to as de Moivre's formula, that actually lets you get a bunch of your trig identities in a nice way. Actually, I'm going to go ahead and share again in order to show that. I should have just gone ahead and done that as we were looking here. And so, all right. So what de Moivre's formula says is that since you have, what is it? Cosine, say, n theta plus I sine n theta, since that would be equal to e to the I theta, I'm sorry, that should have said e to the I n theta, and that is the same as e to the I theta to the n, then this will turn out to be the same as cosine theta plus I sine theta to the nth power. Now, that probably seems like that's not terribly useful here, but if I did n equals 2, just as a quick example, I would have cosine 2 theta plus I sine 2 theta is equal to cosine theta plus I sine theta quantity squared, which is going to be equal to cosine squared theta plus 2I sine theta cosine theta minus sine squared theta. I went ahead and did the foiling in my head there. The minus sine squared is because you've got the I being squared. And that means that this cosine squared theta minus sine squared theta is the real part, which is the cosine 2 theta. And that's the familiar formula that you already know. And 2 sine theta cosine theta is the imaginary part. And that's the familiar formula for sine 2 theta that you already know. So that doesn't seem like a big deal, right? Because you already knew those. But do you remember the formula for cosine 3 theta? Me neither, but that tells it to you. As a matter of fact, there's even, you can even hide the formulas for angle addition and angle subtraction in those as well, so that you have one formula that gets you a bunch of these identities from trig. So, all right, in any case, that's all I have for you. Hope you have a good day.